Today we'll do some problems from the packet that you have. And then on Thursday, we'll do more of work on it, but we'll be working on it individually. Okay? So if you want to ask a question, you can do that. Oh, my geology class, we participated in a webcast so that was just that we were watching them, and you could ask questions, email in questions, and they asked one. So they're right. This is a question from Josh Ring's geology class. That's exciting because we could see him on. Huh? Well, it just happened to fall at the right time on climate change, and that's what we were studying. So you see. So if there's a physics one, we could do it. But all right. So what? Anybody have any questions? Well, then I guess we could just work on it individually if no one has any questions on it. Looks like no one's really done any of it. Let's look at let's go through the rope one. Did we go over the rope one? The last one, section 8. We did that in class together. Did I just do it with you, or did I do it with everybody? Yeah, we did. Okay. You probably. Yeah, so we had to make some changes to that, right? And I put them up on the board there, so you have those. And then I gave you other corrections over there as well. Let's look at 4.7, page 14. Okay? Shows the system in equilibrium with a bar like that and 500 kilograms. And it shows the scale. And the scale's reading 1,000 newtons. Right? Huh? I put that up here. It reads 1,000 newtons. So that's the scale's reading. The scale's reading 1,000 newtons. And then it's connected up here like that at an angle of 45 degrees. We'll just call that tension A. And then over here, it's connected at 70 degrees. That's tension B. And if we draw a free body diagram for it, let's talk about the forces that would be on this. And that's part A, draw a free body diagram. So someone give me one force that's acting on the, and this is a free body diagram for the 500, for the box. Jack. Tension A is one force. So that would be off like that. What's another one? FG is one of them. One of these days, I think it might just smartboard my ball completely off. See how much it's shaking? That's from the train. It's resonance. We'll study resonance later. Yes, it's from the train. Watch, when the train goes by, we'll stop. Well, as a train, it shakes the ground, and if it really matched the natural frequency a lot of this building, then every little shake would be amplified by the next little shake. And that shaking could continue to get really violent, knock the whole building down, but luckily it doesn't match that close, so but it still gets the shaking, comes over here and starts to shake the building. And the building shakes as it goes by. So, and you can see now it's coming to a stop, isn't it? It's still shaking. You can still feel it, but now it stops. All right, so what other forces do we have? TB. Is that it? You gave me one. Mikhail? Well, what's the hint if there's some other force? Yeah, because this 500 kilograms, that's got to give us what? It's going to be 5,000 newtons. So why is the scale reading 1,000 newtons? Because it's hanging, but it's still that the scale is still providing some upward force, 1,000 newtons. What do we call that upward force that the scale is providing? Yeah, it's a support force or a perpendicular force. So F perpendicular is straight up. That's if the scale is compressed as that box is put on it. But if you just looked at what the scale said, you would say, oh, the box weighs 1,000 newtons. Is that true? No. The box weighs 5,000 newtons because it's also attached to ropes. It's kind of annoying. Let's see if it's... Is it any better like this? This is... Speaker was humming. Okay, so... Now... I like to put into the free body diagram with these ones with these tensions off at angles. The tax, right? TAX and the TAY, TAY. See that? And then TBX and TBY. So now I got a free body diagram that has all the stuff that I need to solve the problem, right? Then it says write out the sum of the forces in the y direction. Well, the sum of the forces in the y direction equals 0. So this is our ups equals our downs, right? So give me a force that's going down, Hannah. FG. What other forces are going down? Courtney? It's the only one, so we just have that on that side. What force, give me a force going up? F perpendicular. Give me a force going up, Lorena. TBY. And give me a force going up, Gracie. What? Say it correctly. K. Come on. Thank you. For entertainment purposes? All right. How about some of the forces in the X direction? What's on the left? Elizabeth? There you go. And Mikhail, the other side? TBX. Good. All right. So now we have these sum of the forces. We've written out the expression for the sum of the forces in the y. You could also have said, write out the expression for Newton's first law. Why is that? Right, and that's Newton's first law is the law of equilibrium, right? All right, so we could add some other information into this, though, because 1,000 newtons, nope, sorry. Fg was 5,000 newtons equals F perpendicular, well, that was 1,000 newtons. And TBY, how does TBY, if I wrote it out in terms of TB, what would it be? TB sine 70, right? See that? So I could plug that in. Plus, how is TAY in terms of TA? TA sine 45 degrees. How about TAX? Hex. TA cosine 45 degrees equals TB. How many equations do I have? How many unknowns do I have? Therefore, I can solve. Right. So, we have 5,000 and 1,000, so let's solve this one because it's simpler for TA, okay? So TA would equal, I'll just go to black here, TB cosine 70 degrees over the cosine of 45 degrees. Do you see what I did there? Do you see what I did there? Just divided over the cosine of 45, right? So cos 70 is 0.342. So TA, scroll up a bit, equals TB 0.342, and then cosine of 45 is 0.707. So 0.342 divided by 0.707 is 0.484. So TA is about half a TB, isn't it? See that? Right? Because 0.5 is about a half. 0.484 is about 0.5. So we know that. Now what can we do? We could take this and plug it in, right? So we would have 5,000 newtons equals 1,000 newtons plus TB sine 70 plus, instead of TA, we're going to write TB 0.484 times sine 45. Now let's clean this up a bit. So we can now solve it for TB. Subtract over the 1,000, we get 4,000 newtons. Take the sine of 70, that's 0.94, plus let's multiply sine 45 times 0.484 here. See that? .34. Okay. Now what can we do? Kyle? We could add the TBs, right? Because we have 0.94 TBs and we have 0.34 TBs. So how many total TBs do we have? 0.94 plus 0.34, 1.28 TBs. Then divide by 1.28. TB would be 3,125 newtons. Comes out exact on my nice. TA is TB, times 0.484, but since TB is 3125 times 0.484, we get 1,512.5 newtons. So those aren't so bad, right? That's kind of like these, isn't it? Except we had the scale added in. Let's look at the other project question on there. In section 6. Everybody got this? Page 13, yeah. So that one gives you this crazy design of a thing. The pulley and a string. Attached to another block. Make the block green. And it says the angle of the ramp is 34 degrees. It says the mass of the block is 12 kilograms. It says the mass of the hanging weight is 23 kilograms. And what is the weight of the block on the ramp? Well, first let's draw a free body diagram for both this thing and this thing, okay? So if we look at that, the free body diagram for the hanging mass, what's one thing that we have on it? Whoever. Okay, it's weight force, right? What other forces? Will? There's nothing supporting it. What's that force called? Huh? No. Think of what's holding it up. What? Tension force, yes. Oh, the whole system's in equilibrium. Okay, it says that. Now, let's go to the green block. Free body diagram for that thing. What forces do we have on the green block? Who wants to give me one? Sam. We have friction. Now, if this was allowed to move, this would pull this down. And this would go down, and this would be pulled up. So this would go down, and that would go up if there was no friction. That means that friction is acting against that movement that it would take, which would be up. So the friction is this direction. See that? So you have to think of like which way would the block move. Friction opposes or goes in the opposite direction of the way that the thing would be moving. It's easy if I'm pushing on like this. The friction is what way? Back towards me, right? It's oops. It's a little bit different in this case because if this was like a 500 kilogram thing, then it would pull the whole thing down this way, wouldn't it? And then friction would be that way. So you have to give it thought. Okay. Now, what other forces do we have on it? We have a tension force, and that happens to be the same as this one. So we'll just clone this. Of course, it's not in the same direction, is it? Like that. What other forces? Well, no, they're the same. Well, they're not the same. There's another force. They're not the same. But if you took friction and the component of gravity in the plane, F parallel, right? F parallel plus the friction, since it's in equilibrium, must equal the tension. And that's what we're getting to. Okay? What other forces are on this? Fg for the green block, right? And that comes with it, this component of Fg in the plane, and we call that what? F parallel. What other force do we have? F perpendicular. Okay. Once you have a free body diagram like this, we can calculate what we need. So it says, what is the weight of the block on the ramp? Well, that's this Fg over here. And that would just be m times g, which we know is 230 newtons. Right? Oops. Prep. Sorry. My fault. "12 kilograms." It's the block. It says that. It says the block, not the hanging mass. It says the block. What is the normal force supporting the block? Anybody remember the formula for the normal force? Who wants to tell me? Nope. Elizabeth? F perpendicular equals Fg cosine theta. What is the theta? It's the angle of the ramp. Right. So that would be 120 newtons times the cosine of 34 degrees. (99.5 newtons). Then it says, what is the resultant of the answers from A and B, and what is this force called? Anybody know? It is a net force of, no, you can't just add them like that. Well, they're vectors, right? One of the vectors is this. Whoops. Oh, crap. I mean crust, I'm sorry. One of the vectors is this, right? The other vector is this. If you put them head to tail, what do they sum to give you? F parallel. So the total force, that's why sometimes this F parallel force is also called the total force, because it's the sum of Fg and F perpendicular. But it's also the component of the weight force in the plane, isn't it? Okay, so that, it says what is this called? Well, it's called the parallel force or the total force. And what's our formula for the parallel force? What was the formula for the component of gravity in a plane? G sine theta, right? So what is the component of the force, F parallel force? Fg sine theta, or, yeah. Or you could write mg sine theta, because Fg is mg, right? Fg was 120 newtons, sine of 34 degrees. 67.1 newtons. That's F parallel, but F parallel is also called the total force because it's the sum of F perpendicular plus Fg. Either's fine. What is the tension in the cable connecting the two masses? Well, we can look at this diagram right here, and from this we know that Fg equals what? Ft. So Ft must be Fg, and Fg is mg, which is 23 kilograms times 10 meters per second squared, or 230 newtons. What's the mu value? Well, for that we got to get friction. But if we sum the forces in the plane, equals 0. Okay? That means if we come back up here, what forces do we have going this way on the plane? Ft. That's right. So that means Ft equals, what forces do we have going this way on the plane? Ff plus F parallel. Now Ft we know. We calculated it. 230 newtons. We don't know what Ff is yet. But we know F parallel, which was what? So equals 163 approximately newtons. That's, oh, but we didn't solve the problem yet, did we? Because it wanted mu. What's our formula for friction? Mu times, no, just times F perpendicular. It's only times mg if it's flat, and it's not flat here. So FF is 163, and we found F perpendicular. What was it? 99.5. So the ends are going to cancel, and mu is 1.64. So that just got a good chunk of it off, didn't it? On your reference tables. Now for the next 10 minutes, you can work on your packet. Yeah, but I have